Most nights pass without meaning. You step outside or glance through a window or catch a strip of sky between buildings, and the stars are just there, distant, silent, decorative. They hang above everything, like background noise for the universe. Unmoving and unconcerned, a scattering of pale lights that seem to exist purely for atmosphere. They don't demand anything from you, they don't interrupt your thoughts. They don't appear urgent. They simply exist, steady and calm, as they always have. On a clear night, the sky feels almost gentle. The stars look small, fragile even, like tiny pinpricks pressed into a vast sheet of darkness. They feel far away in a way that makes them irrelevant. Whatever they are, whatever they're doing, it seems disconnected from your life, from your body, from the solid ground beneath your feet. They belong to another realm entirely, one that has nothing to do with deadlines, breathing, aging, or the quiet weight of existing inside a human body. This is how we're trained to see them. As scenery, as symbols, as romantic abstractions. We talk about wishing on stars, navigating by them, writing poems about them. We reduce them to metaphors because metaphors feel safer than reality. A star becomes an idea instead of a thing. A point of light instead of a physical object. Something distant enough that it can't touch us, can't matter to us, can't change anything, and because they look so peaceful, we assume they are. We assume that calm appearance reflects a calm nature. That something so steady, so constant, so quietly beautiful must be simple, harmless, passive. We don't imagine violence when we look at the night sky. We don't imagine chaos or pressure or extremes beyond comprehension. We imagine stillness, we imagine silence. We imagine permanence. There's comfort in that illusion. A quiet sky makes the world feel stable. It suggests that no matter what changes down here, something above it all remains unchanged. The stars feel like witnesses, not participants. Like ancient decorations hung in place long before we arrived, and destined to remain long after we're gone, unaffected by the brief turbulence of human life. So we don't question them. We don't interrogate what they really are or why they exist. We accept them the way we accept mountains on the horizon or clouds drifting overhead. They become part of the background architecture of reality, something to admire occasionally, but never to examine too closely. Something that feels safely removed from us. And yet, that sense of distance is doing something subtle to your mind. It's creating a boundary that doesn't actually exist. A line between out there and in here. Between the universe and you. Between the stars and your own body. It convinces you that whatever happens in the depths of space is separate from the life unfolding behind your eyes. This assumption feels reasonable. After all, the stars don't move, they don't flicker violently. They don't roar or burn or explode in any way you can see. They don't announce themselves as dangerous or powerful. They just shine, quietly, patiently, night after night. Year after year, unchanged within the limits of a human lifetime, but that calm surface is misleading. It's not telling you the truth. It's hiding it, because the universe has a habit of disguising its most extreme processes behind beauty and distance. It lets scale do the work of deception. Things that are unimaginably violent can look serene if they're far enough away. Forces that would tear you apart instantly can appear gentle when reduced to a dot of light against a black sky dot. So when you look up and feel small, detached, and safely uninvolved, you're responding to an illusion created by distance and time. You're seeing a version of reality that has been softened, filtered, and stripped of its intensity by the vastness between you and its source. What reaches your eyes is not the thing itself, but a quiet echo of it. And because of that, it's easy to believe the stars are irrelevant, that they don't concern you. That whatever they are, they have nothing to do with your existence here, now, breathing, thinking, feeling. It's easy to believe they're just part of the scenery, like wallpaper for the night. This belief settles in early. Long before we understand physics or chemistry or time, we learn to separate ourselves from the sky. The ground is where life happens. The sky is where decoration lives. One is active and immediate. The other is distant and symbolic. One matters. The other inspires, but doesn't participate, and yet there's a quiet tension hiding in that assumption. A sense that the story might be incomplete. Because even as the stars seem distant and passive, they refuse to disappear. They persist. They outlast everything familiar. Empires rise and fall beneath them. Entire species appear and vanish while they continue shining, unchanged to the naked eye. That persistence hints at something deeper, something older, something more fundamental than we usually allow ourselves to consider. Still, we rarely follow that hint. We don't ask what kind of process could sustain that light for such lengths of time. We don't ask what kind of environment could produce it, or what kind of consequences it might have. We accept the glow without questioning the cost, and in doing so, we miss the quiet setup taking place. Because the peaceful night sky isn't the truth of the universe. It's the introduction. The calm before an understanding that will rearrange how you see distance, matter, time, and yourself. The stars look passive only because you're standing at the end of a very long chain of events, catching the faintest residue of something far more intense. This moment right now, where the sky feels still and harmless, is the doorway. It's the place where familiarity lulls you into comfort before the illusion breaks. Before the realization that those distant points of light are not decorations at all, but participants in a story that includes you, whether you've noticed it or not. Because the moment you stop seeing the stars as background objects, the moment you stop treating them as distant and irrelevant, the universe just stops feeling like something you live inside of and starts feeling like something you are. Made from. And that understanding begins here, in the quiet and the calm, in the deceptive simplicity of a night sky that has been lying to you in the most beautiful way possible. Equals 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 equals. It doesn't need to deceive you intentionally. It only needs to be distant enough, quiet enough, familiar enough for your mind to fill in the blanks with comfort. Stars do this perfectly. They glow softly. They don't flicker violently. They don't announce their nature. From here, they look gentle, almost fragile, like they could be extinguished by a strong wind if space had air at all. Nothing about them suggests danger or force or intensity. They appear serene because the universe has hidden the truth behind scale. In reality, a star is one of the most violent objects that can exist without immediately tearing itself apart. There is no calm inside a star, no stillness, no peace. Every second, unimaginable forces are locked in a relentless struggle. Gravity is trying to crush the star inward with such strength that, if left unopposed, it would collapse the entire mass into something smaller than a city. At the same time, nuclear reactions in the core are releasing energies so extreme that they are constantly trying to blow the star apart. What you perceive as steady light is the visible result of that balance being maintained, moment after moment, without failure. Calling a star burning is already a misunderstanding. Burning is a chemical reaction. Fire rearranges electrons. Stars operate on a scale where atoms themselves are dismantled. In a star's core, matter is heated to millions of degrees, compressed under pressures that make every earthly comparison meaningless. Hydrogen nuclei are forced together so violently that they fuse, transforming into helium and releasing energy directly from mass itself. Matter doesn't change form. It partially ceases to exist. That loss becomes light. This is not an occasional event, it is continuous. Right now, as you read this, stars across the universe are converting millions of tons of matter into energy every second. Not metaphorically, literally. Entire mountains of mass vanish each moment, replaced by radiation that floods space in all directions. The calm glow you see at night is the afterimage of annihilation happening on an industrial scale, and even that description doesn't fully capture the intensity, because you are never seeing a star as it exists in the present moment. The light reaching your eyes has been traveling for years, decades, sometimes thousands of years. It crossed distances so vast that the human mind cannot intuitively grasp them. That soft point of light may have left its star before your grandparents were born. Some of it began its journey before human civilization existed at all. This means the night sky is not a snapshot. It's an archive. A layered record of stellar history arriving all at once. When you look up, you are not observing reality as it is, but reality as it was, staggered across time by distance. Some of the stars you see no longer exist in the form you're seeing. They may have expanded, collapsed, or exploded long ago. Their light simply hasn't caught up with that fact yet. Distance doesn't just make things look smaller, it makes them look quieter. It strips away motion, violence, urgency. An explosion seen from far enough away doesn't look like an explosion at all. It looks like a flicker, a glow, a steady presence. The universe relies on this effect to hide its extremes. The most destructive processes ever known are softened into something your nervous system can tolerate. If you were close enough to a star to see it as it truly is, the illusion would collapse instantly. You wouldn't see a glowing orb. You'd see a surface of roiling plasma, torn apart by magnetic fields, erupting in flares that dwarf planets, throwing arcs of matter into space at speeds that defy intuition. You'd feel radiation intense enough to shred molecules, heat powerful enough to vaporize matter before it could react. There would be no beauty in the human sense. Only force, but you are never allowed that proximity. Space protects you from the truth by stretching it thin, by letting time and distance dilute violence into elegance, by turning annihilation into starlight. That transformation is why stars are so easy to misunderstand. We associate brightness with warmth, warmth with comfort, and comfort with safety. We mistake stability for gentleness. We forget that stability can exist at terrifying extremes, maintained not by kindness, but by perfect balance between opposing catastrophes. And then there's the most unsettling part. That light isn't just energy, it's information. Every photon carries a record of the conditions that created it. The temperature, the reactions, the density, the physics of its origin are encoded in its wavelength. When that light reaches your eyes, you are intercepting data from a nuclear furnace that existed long before you were here. You are not simply seeing a star. You are receiving a message from deep time. This reframes the night sky entirely. It is not a ceiling above your life. It is a cross-section through history, a mosaic of ancient events still echoing through space. Each point of light is evidence that something unimaginably violent happened, and that its consequences are still unfolding. The peacefulness you feel when you look up is real, but it is misplaced. It belongs to your position, not to the stars themselves. You are standing at a safe distance, shielded by scale, interpreting catastrophe through beauty. The universe is not calm, it is controlled. And control at that scale requires forces that dwarf anything you associate with the word violent. Once you understand this, the stars can never go back to being decorative. They stop being symbols and start being processes. They stop being distant and start being historical. The night sky becomes active, restless, alive with ongoing transformation rather than static beauty, and this is the moment where the illusion truly breaks. Because if stars are not gentle, and their light is not present, and their calm is not real, then the boundary you thought existed between their world and yours begins to dissolve. The violence you believed was safely contained out there has already reached you. It has simply been translated into a form gentle enough to touch your skin, warm your planet, and enter your eyes without destroying you. What looks like serenity is survival at a distance. What looks like decoration is the residue of creation and destruction playing out on scales beyond comprehension. The stars were never passive. They were never irrelevant. They were simply far enough away for you to believe they were. Time behaves differently when distance becomes large enough. In everyday life, you experience time as something immediate and local. A second passes, then another, cause follows effect. Light turns on when you flip a switch. Sound arrives almost instantly. After something moves, reality feels synchronized. But the moment you lift your eyes to the night sky, that synchronization quietly collapses. Even if you don't notice it happening, every star you see is already telling you a story from the past. Not metaphorically, literally, light does not arrive instantly. It travels at a finite speed, fast by human standards, but painfully slow when measured against cosmic distances. Even the nearest stars are so far away that their light takes years to reach you. That means the night sky is never showing you what exists now. It is showing you what once existed, preserved and delayed by space itself. This is difficult to feel intuitively because your brain evolved in a world where delays are negligible. You are not wired to experience light as historical data. You are wired to experience it as presence. When something is visible, you assume it is happening now. That assumption works on Earth. It fails completely once space enters the picture. When you look at a star that is 10 light-years away, the light entering your eyes tonight began its journey a decade ago. It left that star when the world was different, when events you remember had not yet happened, when parts of your own life had not yet unfolded. You are seeing an event that has already concluded. The star may be unchanged, or it may not. You have no way of knowing from sight alone. Some of the stars visible to the naked eye are hundreds or thousands of light-years away. Their light began traveling toward Earth before recorded history, before cities, before agriculture, before language in its modern form. Civilizations rose and fell while those photons crossed the void. Empires existed for their entire lifespan in the time it took that light to travel a fraction of the distance it still had left. And this creates a strange situation. You are standing firmly in the present, but your eyes are not. Your vision extends backward in time without your permission. The night sky is a collage of different eras layered on top of each other, a mix of moments that never coexisted. Some stars you see are young in cosmic terms. Others are ancient. Some may already be gone, their light still en route, unaware that its source has changed forever. This means that when you look up, you are not observing a place. You are observing a timeline. The sky is not a window. It is a record. Each point of light is a timestamp, a delayed message sent long before you were here. You are intercepting it mid-journey, long after it left its origin, long before it reaches its end. The universe is constantly communicating with you, but it speaks in a language stretched across time. This reframes what a star even is. It stops being an object you look at and becomes an event you are witnessing late. The star's light is not its current state. It is its memory. And the farther away it is, the older that memory becomes. Some of what you see tonight began its journey before Earth itself formed. Ancient light, finally arriving, finally being seen. There is something unsettling about this once it sinks in. The present moment feels solid because you believe it is shared, that what you see exists now, alongside you. But the night sky breaks that illusion. It shows you that reality is not synchronized across distance, that the universe has no single now. Every location exists in its own slice of time, and what you perceive is always delayed. The sky becomes a natural time machine, one that doesn't require imagination or speculation. It works automatically. You don't step into it. It pours into you. Every photon that reaches your eyes has survived a journey so long that entire worlds could change while it traveled. And now it ends that journey inside your vision, inside your awareness, completing a path that began long before you had a name. This is why stars can feel eternal. Not because they don't change, but because you never see them change. Their transformations are hidden behind the speed of light. A star can explode in a supernova, tearing itself apart in a moment of cosmic violence, and you would continue seeing it as calm and stable for centuries afterward, unaware that what you're looking at no longer exists. You're always late to the universe. That lateness creates a sense of mystery that no telescope can fully erase. Even with our best instruments, we are still seeing history. More detailed history, perhaps, but history all the same. The universe never shows itself live. It only shows recordings. And yet those recordings are not meaningless. They are precise. Light carries information encoded in its color, its intensity, its spectrum. From that information, we can reconstruct temperatures, motions, reactions. We can read the past with extraordinary accuracy. We can know what was happening inside a star millions of years ago by analyzing the photons that finally reach us now. So the night sky becomes something astonishing. Not just beautiful, not just distant, but informative. A vast archive written in light. A history book that takes billions of years to read because every page arrives slowly, one photon at a time. Once you understand this, the act of looking up changes. You are no longer just observing space. You are observing duration. You are seeing consequences unfold long after their causes. You are watching the universe remember itself. And somewhere in that realization, time itself starts to feel less rigid, less absolute. You begin to sense that the present moment is not a universal condition, but a local experience. That now only exists where you are, and everywhere else exists slightly before it. The stars don't just light the night. They dissolve the idea that reality happens all at once. They reveal a universe stretched across time, layered, asynchronous, vast beyond the comfort of immediacy. When you stand beneath them, you are surrounded not by distant objects, but by ancient messages arriving all at once, telling you what the universe was, not what it is. And that understanding opens a door. Because once you accept that light carries history, you begin to wonder what else it carries, and what role you play in receiving it. You are not just looking at the past. You are part of the process that allows the past to be seen at all. Most people grow up believing stars burn. It's a reasonable assumption. Fire is familiar. We know what it looks like, what it feels like, how it behaves. Flames consume fuel, release heat and light, then fade when the fuel runs out. When we see something glowing in the sky, calling it fire feels intuitive. But this intuition is wrong in a way that matters because it replaces reality with something far smaller, far gentler, and far less strange than what is actually happening. A star is not a fire. Fire is chemistry. It rearranges electrons. It depends on oxygen. It releases energy stored in chemical bonds. Even the largest inferno on Earth is operating within limits set by molecules. A star ignores all of that. Inside a star, chemistry is irrelevant. Molecules cannot exist. Atoms barely survive. What powers a star happens at a deeper level, where matter itself becomes unstable under pressure. At the core of a star, temperatures rise into the millions of degrees. Pressure becomes so extreme that ordinary comparisons stop working. Gravity crushes matter inward with such force that atomic nuclei are forced into close contact. Under normal conditions, those nuclei repel each other violently, like charges, resist being pushed together. But inside a star, the conditions are so intense that this resistance is overwhelmed. Nuclei collide again and again until, occasionally, they merge. This is nuclear fusion. Hydrogen nuclei combine to form helium. And when they do, something subtle but profound happens. The helium nucleus that forms has slightly less mass than the hydrogen nuclei that created it. That missing mass does not disappear quietly. It is converted directly into energy. This is what Einstein's equation describes. E equals mc squared is not an abstract insight or a theoretical curiosity. It is a statement about what stars are doing right now. Every second, in every star you can see, mass is being transformed into energy as a matter of routine. Not symbolically. Not metaphorically. Physically. The speed of light squared is an enormous number. That means even a tiny amount of mass releases an extraordinary amount of energy when converted. Stars exploit this fact relentlessly. They are machines built by gravity to convert matter into light with staggering efficiency. In the core of our own sun, millions of tons of matter are lost every second, transformed into radiation that floods outward through space. And yet, from a distance, this process looks calm, steady, predictable. That steadiness hides the scale of what is happening. If you tried to reproduce even a fraction of this energy on Earth, you would fail instantly. Our most powerful weapons, our largest reactors, our most ambitious technologies barely register when compared to the output of an ordinary star. What makes this even more unsettling is that stars do this continuously. They do not flare once and stop. They do not explode immediately. They maintain this conversion second after second, year after year, for billions of years. Gravity and fusion hold each other in perfect opposition. Gravity pushes inward. Fusion pushes outward. If either side gains even a slight advantage, the star responds automatically, adjusting its size and temperature to restore balance. This balance is not gentle. It is precise. A star exists on a knife edge between collapse and explosion. The reason it doesn't tear itself apart is not because the forces are weak, but because they are perfectly matched. Stability at this scale is not calmness. It is tension sustained without failure. When you understand this, the idea of a burning star becomes embarrassingly inadequate. Fire flickers. Stars endure. Fire rearranges matter. Stars erase it. Fire is temporary. Stellar fusion can persist longer than the current age of the universe. One is a surface phenomenon. The other reshapes the cosmos. And the light that escapes from a star is not excess. It is the unavoidable consequence of this process. Energy produced in the core must go somewhere. It begins a slow journey outward, scattering, colliding, changing direction countless times before finally escaping into space. That light then travels across vast distances until, by chance, a tiny fraction of it intersects with your eyes. When it does, you are not seeing a flame. You are seeing the result of mass loss that happened long ago. You are seeing energy that was locked inside matter, freed under conditions so extreme that the matter itself could not survive intact. This reframes the meaning of starlight entirely. It is not decoration, it is evidence. Evidence that the universe is capable of converting matter into energy on scales that defy everyday comprehension. Evidence that reality operates far beyond the comfort zone of human intuition. Once you grasp this, the stars stop being romantic objects and start being physical processes. They stop being distant symbols and start being engines. They are not burning in the sky. They are dismantling themselves, slowly, methodically, turning mass into illumination, and this dismantling is not a flaw. It is the point. Without it, nothing heavier than hydrogen would exist. Without it, planets could not form. Chemistry could not proceed. Biology could not emerge. The very atoms that make complexity possible are born from this relentless conversion. So, when you hear E equals mc squared, you are not hearing a formula. You are hearing a description of an ongoing transformation that has shaped the universe for billions of years. You are hearing the reason stars shine, the reason matter changes, the reason energy flows. A star is not fire. It is far stranger than that. It is a place where matter forgets how to remain matter, where mass becomes light, and where the universe pays the cost of illumination by slowly dismantling the things that create it. Creation is often imagined as something gentle. We picture growth as gradual, orderly, and kind. Seeds sprout. Life unfolds. Complexity feels like the natural result of time and care. But this image comes from living inside a narrow window of conditions where gentleness is possible. It does not reflect how complexity actually arises at the deepest levels of reality. The universe does not build intricate things by being careful. It builds them by applying pressure until simpler structures break. Nothing complex forms in comfort. Comfort preserves what already exists. It stabilizes. It prevents change. If the universe were gentle everywhere, it would still be filled with little more than diffuse gas, evenly spread and eternally uneventful. Complexity requires imbalance. It requires regions where forces overwhelm resistance, where matter is pushed far beyond the conditions it prefers. Pressure is the first requirement. Gravity must pull matter together with enough force to overcome its tendency to drift apart. Left alone, atoms spread out. Disorder increases. Nothing assembles itself willingly. Collapse is not a failure of the universe. It is the mechanism by which anything structured can exist at all. Without collapse, there are no stars. Without stars, there are no heavy elements. Without heavy elements, there is no chemistry capable of complexity. Heat follows pressure inevitably. When matter collapses, energy has to go somewhere. Motion increases. Collisions become violent. Temperature rises. Heat is not an accessory to creation, it is its byproduct. The universe does not choose heat. It accepts it as the cost of forcing matter into new arrangements. Inside stars, this process is taken to its extreme. Pressure reaches levels that crush atomic structures. Heat climbs so high that matter becomes plasma, stripped of its familiar properties. Atoms lose their identities. Electrons are torn away. Nuclei slam together again and again. This is not refinement, it is assault. And from that assault, new elements emerge. Gentleness cannot do this. No amount of patience, no span of time, no soft influence can convince hydrogen to become carbon. The transformation requires violence. It requires temperatures where atoms cannot remain intact and pressures that overwhelm fundamental repulsion. Complexity is not coaxed into existence. It is forced. This is uncomfortable to confront because it challenges a deeply held belief about how progress works. We like to imagine that better things arise from kinder processes, that evolution trends toward harmony, that the universe prefers stability and comfort. But the evidence points in the opposite direction. The universe is indifferent to comfort. It does not avoid extremes. It relies on them. This indifference is not malicious, it is structural. The laws of physics do not care whether a process feels violent or gentle, they only respond to conditions. If the conditions are sufficient, transformation happens. If they are not, it doesn't. There is no preference for ease. There's only inevitability. Even the elements that make life possible exist because matter was once subjected to conditions lethal to anything resembling life. The carbon in your body required temperatures so high that molecules could not exist. The iron in your blood required pressures found only in the cores of massive stars moments before they collapsed. The calcium in your bones was forged in environments where the concept of bone would be meaningless. This means that complexity is always downstream of destruction, not as a poetic metaphor but as a physical rule. Simpler structures must be broken before more intricate ones can form. The universe advances by dismantling what is stable enough to exist under gentler conditions and rebuilding it under harsher ones. Stars themselves are evidence of this principle. They are born from collapse, sustained by tension, and eventually destroyed when balance fails. At every stage, extremes drive change. There is no peaceful phase where complexity quietly accumulates. There is only a sequence of pressures applied until a new outcome becomes unavoidable. This reframing is unsettling because it removes the universe from moral narratives. Creation is not reward. Destruction is not punishment. They are paired outcomes of the same processes operating without intention. Comfort is irrelevant. Survival is incidental. Complexity is rare precisely because the conditions required to produce it are hostile. Once you accept this, the universe stops looking benevolent or cruel and starts looking honest. It does not soften its methods for the sake of what comes next. It does not protect emerging structures from the forces that created them. It allows outcomes to exist only if they can endure the conditions that brought them into being. This has implications far beyond stars. It suggests that existence itself is conditional, that everything complex is temporary, balanced precariously between forces that can dismantle it at any moment. Stability is not guaranteed. It is negotiated continuously under pressure. And yet, from this indifference comes everything that matters. Not because the universe intends meaning, but because meaning can arise only where conditions were once severe enough to make complexity possible. The very fragility of structured things is a consequence of the extremes required to create them. Gentleness maintains. Extremes transform. The universe does not confuse the two. What looks harsh from the inside is simply the universe doing what is required to move beyond simplicity. Pressure, heat, collapse, these are not aberrations. They are the price of complexity. And everything you recognize as structure, order, or life exists because that price was paid, again and again, without hesitation. Stars do not live the same kind of existence. They follow the same physical laws, begin from similar raw material, and obey the same fundamental rules, but their paths diverge almost immediately based on one factor alone: mass. That single difference determines everything that follows. How long they shine, how violently they change, how they end. There is no choice involved, no flexibility, no adjustment later on. From the moment a star forms, its fate is already written into its size. Small stars live quietly, not peacefully in a human sense, but steadily. Their gravity is strong enough to ignite fusion, but not strong enough to force it to happen at extreme rates. The pressure in their cores is moderate by stellar standards. Reactions proceed slowly. Fuel is consumed with restraint. These stars are efficient, almost conservative, converting their hydrogen into energy at a pace that allows them to persist for extraordinary lengths of time. A small star can shine for hundreds of billions, even trillions of years. Longer than the universe has existed so far. Entire cosmic eras will come and go while these stars remain largely unchanged. Galaxies will drift apart. Larger stars will be born and die in waves. Still, the smallest stars will continue there. Slow, steady output, barely altered by the passage of time. Massive stars exist at the opposite extreme. Their gravity is overwhelming. It compresses their cores to extraordinary densities, driving temperatures far higher than those in smaller stars. Fusion in these environments happens at ferocious rates. Fuel is not sipped, it is consumed. These stars shine with immense brightness, releasing enormous amounts of energy. But they pay for that brilliance with time. A massive star may live only a few million years. Compared to the lifespan of small stars, this is almost nothing. These stars race through their fuel because their own gravity leaves them no alternative. Their cores are under such intense pressure that fusion reactions accelerate uncontrollably. The more massive the star, the more violently it burns, and the shorter its existence becomes. This contrast creates a kind of narrative structure without intention or emotion. Small stars endure, massive stars blaze. Neither strategy is chosen. Both are imposed by physics. A star cannot decide to slow down or speed up. It responds automatically to the forces acting upon it. Size dictates tempo. Tempo dictates destiny. This inevitability is one of the most striking aspects of stellar evolution. There are no exceptions. A star's mass sets boundaries that cannot be crossed. A small star will never explode as a supernova. It simply lacks the gravitational pressure required to reach that stage. A massive star will never fade gently. Its internal conditions guarantee instability once its fuel runs out. The universe does not negotiate outcomes. It allows processes to unfold according to scale. And scale is unforgiving. This makes stellar life cycles feel strangely familiar without being human. There is progression, change, and conclusion, but no intention behind them. A star does not strive to last longer or burn brighter. It does what its mass compels it to do. Stability persists until it cannot. Collapse happens when support fails. Everything follows from initial conditions set long before the star begins to shine. Even within these broad categories, the differences are stark. Medium-sized stars like the one that warms your planet occupy a narrow middle ground. They burn. Neither too fast nor too slow. Their lives last billions of years, long enough for complex structures to form around them, long enough for chemistry and biology to unfold on nearby worlds. This balance is not typical. It is a consequence of being neither too large nor too small. Massive stars dominate their environments while they exist. Their intense radiation shapes nearby space, stripping matter from other forming stars, altering the chemistry of entire regions. They live fast, change rapidly, and die dramatically. Their deaths release more energy in a single event than they emitted during their entire lives. They are brief, but transformative. Small stars are the opposite. They change little, influence their surroundings gently, and persist far beyond the epochs that produced them. They do not reshape galaxies in moments. They quietly maintain light in a universe that would otherwise grow dark. Long after the brightest stars have vanished, these small furnaces will remain, glowing faintly but reliably. None of this is about character or purpose. It is about thresholds. About what happens when matter crosses certain limits. Add mass and gravity strengthens. Strengthen gravity and pressure increases. Increase pressure and fusion accelerates. Accelerate fusion and fuel disappears faster. The entire story unfolds as a chain of consequences, each step locked to the one before it. This is why scale matters so profoundly in the universe. Small changes at the beginning produce radically different outcomes over time. A slight increase in mass can shorten a star's life by billions of years. A slight decrease can extend it beyond the lifespan of galaxies. These differences are not subtle. They are absolute, and this is what gives stellar evolution its narrative weight. Not because stars experience their lives, but because their trajectories are shaped by the same kind of inevitability that governs all complex systems. There is growth, transformation, and termination, but no escape from the underlying constraints. You look at the sky, you are seeing stars at different stages of this process. Some are young, newly ignited. Some are mature, stable, and unchanging on human timescales. Others are nearing the end of their fuel, quietly preparing for transitions that will reshape their structure entirely. You are witnessing a population of objects moving through predetermined paths at vastly different speeds. The diversity is not accidental. It is the result of scale applied repeatedly across enormous numbers. Every star follows the same basic rules, but those rules play out differently depending on how much matter was available at the beginning. The universe explores every possible outcome simply by varying size. This makes the night sky a map of inevitability, rather than intention. There is no drama in the human sense, no triumph or failure. There is only the unfolding of physical law, expressed through objects large enough to make those laws visible. Stars do not live meaningful lives. They live consequential ones. Their size determines their influence, their duration, and their end. Some endure quietly for incomprehensible spans of time. Others burn so intensely that they cannot avoid destruction. Neither path is preferable. Both are necessary. Together, they ensure that the universe does not stagnate, that light exists across vast timescales, that elements are produced, scattered, and recycled. That change continues. In that sense, stellar evolution is not a story about stars at all. It is a demonstration of how scale governs destiny, how initial conditions dictate outcomes, and how complexity emerges not from choice, but from constraint. Some stars are too much from the moment they exist. Too massive, too intense, too powerful to remain stable for long. These are the hypergeans, objects so large and luminous that their very brightness is a warning rather than a feature. They dominate their surroundings not quietly, but aggressively, pouring out energy at rates that defy any ordinary sense of scale. Where smaller stars conserve, hypergeans spend. Where moderate stars endure, hypergeans accelerate toward their own undoing. A hypergean forms when an enormous amount of matter collapses into a single object. Gravity becomes overwhelming, compressing the core to extreme densities and driving temperatures skyward. Fusion ignites not gently, but explosively, and once it begins, it cannot slow down. The star's mass forces the reactions to proceed at ferocious rates. Fuel is consumed not over billions of years, but over millions, sometimes less. From the outside, this looks like brilliance. From the inside, it is unsustainable. These stars shine with the light of hundreds of thousands, sometimes millions of suns combined. Their surfaces are unstable, roiling with convection and torn by radiation pressure so intense that matter struggles to remain bound. Vast amounts of material are blown away in stellar winds, peeling layers off the star even as its core continues to burn ever hotter. A hypergean is not merely losing energy. It is actively dismantling itself. Brightness in this context is not success. It is expenditure. Every photon that escapes carries energy that had to come from somewhere, and that somewhere is the stars. Onnas. The more intensely a star shines, the faster it erases itself. Hypergeans glow with reckless output, and the cost is paid immediately. Their fuel reservoirs, enormous though they are, vanish at astonishing speed. There is a tragic symmetry to this process. The very mass that allows hypergeans to become so luminous also guarantees their instability. Their gravity is too strong. Their cores too compressed, their fusion reactions too fast. They cannot find a long-term balance. They exist in a state of permanent excess, always burning more intensely than they can afford. This excess shapes everything around them. Nearby gas clouds are blasted apart by radiation. Forming stars are stripped of material before they can fully develop. Entire regions of space are transformed by the presence of a single hypergean. These stars do not coexist gently with their environments. They overwhelm them, and yet this dominance is fleeting. A hypergean's life is measured not in the slow march of cosmic time, but in brief, violent chapters. Millions of years may sound long, but on stellar scales it is a blink. While smaller stars will continue shining long after galaxies themselves have changed shape. Hypergeans race through every stage of their evolution with terrifying speed. As their fuel is consumed, their internal structure becomes increasingly unstable. Fusion moves through heavier and heavier elements, each stage releasing less energy than the last. The star compensates by increasing pressure and temperature, accelerating the process even further. What looks like sustained brilliance from a distance is, internally, a countdown. There is no recovery phase, no slowing down, no gentle decline. Once a hypergean reaches this stage, collapse is inevitable. The core grows denser and hotter, fusion races forward, and gravity tightens its grip. The star's own mass becomes its executioner. From afar, none of this is visible. A hypergean can look calm, even majestic, hanging in space as a brilliant beacon. But that appearance is deceptive. The light reaching your eyes is already outdated, already behind the internal reality. By the time you see a hypergean shining steadily, the processes that will destroy it may already be irreversible. This is the cruelty of scale. Distance turns catastrophe into beauty. Time delay turns collapse into serenity. A star can be in its final moments while appearing unchanged to any observer far enough away. The universe hides its most violent stories behind elegance and light. When a hypergent finally fails, it does not fade. It erupts. The balance between gravity and fusion collapses in an instant, and the star's core implodes. What follows is one of the most energetic events the universe can produce. In a supernova, the star releases more energy in seconds than it did over its entire life. Matter is torn apart, accelerated to incredible speeds, and hurled into space, carrying with it the elements forged in the star's core. This ending is not accidental. It is the direct consequence of excess. Hypergents are not unlucky stars. They are stars that cross the threshold from which there is no stable return. Their size made restraint impossible. Their brightness guaranteed their demise. There is a stark contrast here with smaller stars that sip their fuel and persist quietly. Where hypergents burn themselves out in a blaze of short-lived glory, smaller stars endure in relative anonymity, shaping the universe slowly rather than violently. One path is explosive and brief. The other is steady and prolonged. Both arise from the same laws, applied at different scales. The spectacle of hypergents is undeniable. They are among the brightest objects in the cosmos, visible across immense distances, their light dominating entire regions of space. But this spectacle is inseparable from destruction. To shine that brightly is to accelerate toward collapse. To command that much energy is to shorten existence dramatically. This is why brightness, at cosmic scales, is never free. It is borrowed from the future. Every moment of intense luminosity subtracts time from what remains. Hypergents live fast not by choice, but by necessity. Their mass leaves them no alternative. In this way, hypergents embody a fundamental truth about excess. Beyond certain limits, power becomes self-destructive. Systems that cannot moderate their output consume themselves. What looks like dominance is often fragility expressed at scale. The universe does not intervene. It does not temper these stars or preserve them for their beauty. It allows the process to unfold exactly as the physics demands. Excess is punished, not morally, but mechanically. When output exceeds sustainability, collapse follows. And yet, this self-destruction is not meaningless. The violent deaths of hypergents seed space with the heavy elements that make complexity possible. Their brief, intense lives enrich the cosmos in ways slow, enduring stars cannot. They burn themselves out, but in doing so, they transform everything around them. Hypergents are not warnings written for human interpretation. They are demonstrations. Proof that at cosmic scales, brilliance is inseparable from cost, and that the brightest lights often burn for the shortest time. Some stars choose patience simply by being small. Not by intention, not by restraint, but by physics. These are red dwarfs, the most common stars in the universe and the least dramatic. They do not dominate the sky. They do not burn brilliantly. They do not announce themselves with spectacle. Most are invisible to the naked eye, lost among brighter neighbors. And yet, in terms of endurance, nothing else comes close. A red dwarf forms with only a fraction of the mass of stars like the Sun. That single difference changes everything. Its gravity is weaker, its core is cooler. Fusion proceeds slowly, almost reluctantly, compared to the furious pace inside massive stars. Hydrogen is converted into energy at a rate so modest that the star barely seems to age at all. Where larger stars race through their fuel, red dwarfs conserve it. They burn carefully, efficiently, extracting energy from hydrogen with minimal waste. The result is a lifespan that stretches beyond anything human intuition is equipped to handle. Not billions of years, trillions. To understand what that means, you have to step back from familiar scales entirely. The universe itself is about 13.8 billion years old. That number already exceeds any meaningful human frame of reference. Entire histories fit comfortably inside it. And yet for a red dwarf, that span of time represents only the opening moments of its existence. Not a single red dwarf has ever died of old age. The universe simply hasn't been around long enough. Every red dwarf that has ever formed is still shining today. Every one. Some have been glowing steadily since the earliest eras of cosmic history, unchanged, unhurried, quietly converting hydrogen into light while galaxies assembled, collided, and drifted apart. While massive stars lived fast and vanished, red dwarfs Endured. Their patience is structural. Because they are small, their cores never reach the extreme temperatures that force stars into rapid fusion. Pressure remains manageable. Reactions remain slow. Nothing pushes them toward instability. They exist in a state of near-permanent equilibrium, balanced so effectively that change becomes almost imperceptible. This endurance reshapes how the future of the universe looks. Long after stars like the Sun expand, shed their outer layers, and fade into remnants, red dwarfs will still be there. Long after the brightest galaxies dim, these small stars will continue glowing faintly, providing the last sources of light in a universe growing colder and darker. There is something quietly unsettling about this. Red dwarfs do not participate in the dramatic cycles of birth and death that characterize larger stars. They do not explode. They do not seed space with heavy elements through violent endings. They simply persist. They outlast. In a far future where most stars have burned out, where space has stretched so much that galaxies exist in isolation, red dwarfs will remain as cosmic embers. Not bright, not commanding, but present. They will define an era measured not in billions, but in trillions of years. This scale forces a recalibration of meaning. Human history, already a blink against the lifespan of the universe, becomes vanishingly small next to a red dwarf's life. Civilizations rise and disappear in spans too short to register. Even entire species become transient phenomena. Against this backdrop, endurance loses any emotional framing and becomes purely physical. Red dwarfs do not hurry because there is nothing requiring them to. Their mass allows stability without urgency. They are not under pressure to evolve quickly or collapse dramatically. They simply exist, sustained by slow reactions and modest output, indifferent to the passage of time as humans understand it. This does not make them gentle in a comforting sense. Their environments can be harsh. Planets orbiting close enough to receive warmth may be locked into permanent day and night, exposed to flares that can strip atmospheres. Endurance does not imply kindness. It implies persistence. What red dwarfs offer instead is a different vision of cosmic time. One where change is measured in incomprehensible spans, where the future stretches far beyond any story involving humans, Earth, or even familiar galaxies. They represent a universe that is in no hurry to conclude itself. In that distant future, when red dwarfs finally exhaust their hydrogen, their endings will be quiet. No explosions, no dramatic collapse. They will slowly cool, fading into darkness, over spans of time that dwarf even their already vast lifetimes. Their deaths will be less events than gradual absences. This quiet conclusion contrasts sharply with the violent deaths of massive stars. Where hypergents end in spectacular explosions that reshape space, red dwarfs end by simply running out of momentum. Their fuel dwindles, their light fades. The universe grows darker by degrees rather than shocks. Together, these paths reveal something essential about scale. Excess produces spectacle and brevity. Moderation produces longevity and silence. Neither path is chosen. Both are consequences of mass interacting with physical law. Red dwarfs remind you that the universe is not optimized for drama. It is optimized for process. Some processes are explosive. Others are slow beyond imagination. The universe accommodates, both without preference. When you consider that the future of light belongs largely to these small stars, the cosmos begins to feel less like a story racing toward an ending and more like a long, gradual cooling. A place where activity does not stop abruptly, but thins out over unimaginable durations. This perspective dissolves urgency. It replaces it with patience that is not comforting, but clarifying. The universe is willing to wait longer than any outcome requires. It does not rush creation or destruction. It allows processes to run their full course, however long that takes. Red dwarfs are monuments to that patience. They do not dazzle, they endure. And in doing so, they redefine what longevity means on a cosmic scale. They will be the last witnesses when most light has faded. Not observers in any conscious sense, but physical reminders that stability, once achieved at the right scale, can persist far beyond expectation. In their quiet persistence, red dwarfs reveal a universe that measures time differently than you do. One that is comfortable with trillions of years, with slow transformations, With futures so distant, they lose all narrative shape, standing beneath the night sky. It is easy to focus on the brightest stars, the most dramatic ones. But the long future belongs to the faint. To the stars that refuse spectacle. To the ones that simply continue. Not everything in the universe succeeds. This is easy to forget when most of what we talk about is what exists, what shines, what endures. But between stars and planets, between ignition and darkness, there are objects that occupy a quieter category. Brown dwarfs are not stars, but they are not planets either. They exist in the narrow space between outcomes, formed from the same processes as stars, yet stopping just short of becoming one. A brown dwarf begins the same way a star does. A cloud of gas collapses under gravity. Matter gathers. Pressure increases. Heat builds. For a time, everything looks familiar. From the outside, there is no clear signal that anything will be different. The process unfolds as expected, moving toward ignition, but then it stalls. The mass is not quite enough. The pressure does not quite reach the required threshold. Fusion never fully takes hold. This is not a dramatic failure. There is no explosion, no collapse. No decisive moment where the universe announces that something has gone wrong. The process simply runs out of momentum. The object settles into a state of partial becoming, forever defined by what it almost achieved. Brown dwarfs confuse a heavier form of hydrogen for a short time, releasing some energy, glowing faintly in their early lives. But they cannot sustain the reactions that define true stars. Once that limited fuel is gone, they cool and fade slowly, drifting toward invisibility. They never ignite fully. They never shine steadily. They never cross the line. That line is thin. Thinner than intuition would suggest. A relatively small difference in mass determines whether an object becomes a long-lived star or a dim, cooling remnant. Add a little more material, and fusion becomes self-sustaining. Remove a little, and it never truly begins. There is no gradual transition, no compromise state. Physics is unforgiving in this way. Thresholds are absolute. This is where the idea of imperfection enters the picture. Not as error, but as outcome. The universe does not correct near misses. It does not smooth rough edges or provide second chances. If conditions are sufficient, transformation occurs. If they are not, it doesn't. Brown dwarfs are the record of that indifference. They are numerous. Possibly more common than stars themselves. The galaxy may be filled with them, drifting quietly through space, dark and difficult to detect. They contribute little light. They shape nothing on large scales. They exist without spectacle, without consequence, without recognition. And yet, they are deeply informative. Brown dwarfs reveal how narrow the pathways to complexity really are. They show that most attempts at becoming something more do not quite make it. For every star that ignites and shines for billions of years, there may be countless objects that gather, collapse, and then simply stop. The universe is not optimized for success. It is structured around thresholds, and most things fall short of them. This challenges a comforting narrative. We like to imagine the universe as efficient, purposeful, inclined toward formation. But brown dwarfs suggest otherwise. They suggest a cosmos where outcomes are distributed unevenly, where only a subset of attempts cross the necessary boundaries, and where near success is not rewarded with continuation. There is something liminal about these objects. They hover between categories, never fully belonging to either, too massive to be planets, too small to be stars. They occupy a permanent in-between state, defined not by what they are, but by what they fail to become. This almostness carries weight. It reminds you that existence is not binary, not cleanly divided into success and non-existence. There are gradients, margins, outcomes that persist without fulfillment. The universe is filled with things that exist without completing the transformations they were moving toward. Brown dwarfs are not tragic in any emotional sense. They do not experience loss or frustration. But their presence introduces a subtle realism into the story of the cosmos. Not everything evolves into something brighter. Not every process culminates in complexity. Some trajectories simply plateau and fade. This is not inefficiency. It is consequence. From a distance, a brown dwarf may look indistinguishable from a small star. Only careful measurement reveals its nature. This blurring of categories reinforces the idea that outcomes are not always obvious. That what looks like success from afar may already be constrained by limits that guarantee a quieter future. Over time, brown dwarfs cool. Their initial heat radiates away. Their faint glow dims. Eventually, they become cold, dark objects, nearly invisible against the background of space. They persist, but without presence, without impact, without contribution to the next cycle of stellar creation, and yet, they are not erased. They remain as evidence. Evidence that formation alone is not enough. That collapse does not guarantee ignition. That the universe allows incomplete stories to exist indefinitely. This has implications beyond astronomy. It suggests that the line between radically different outcomes can be narrow, arbitrary, and indifferent to effort. Small differences in initial conditions can lock systems into entirely different futures. Once crossed, those thresholds cannot be negotiated. Brown dwarfs sit on the wrong side of one such threshold, not by mistake, not by chance in any meaningful sense. Simply because the conditions were insufficient. Gravity pulled, but not hard enough. Heat built, but not high enough. Fusion approached, but did not persist. The universe does not care that the difference was small. It does not care that the object came close. Physics does not scale sympathy with proximity. In this way, brown dwarfs quietly dismantle the idea that the universe is shaped only by its brightest outcomes. They reveal a background population of objects defined by limitation rather than expression. By restraint imposed from the outside, not chosen from within, they also remind you that the night sky is selective. You see stars because they shine. You do not see brown dwarfs because they do not. Visibility becomes a filter that shapes perception. What is common can be hidden. What is rare can dominate attention. There may be billions of brown dwarfs passing silently through the galaxy, unnoticed, unremarked upon, contributing nothing to the spectacle of the sky. Their existence does not alter the story of light. It complicates it. They represent paths that nearly worked, futures that almost unfolded, processes that gathered momentum and then lost it. In a universe defined by thresholds, almost is not enough. This does not make brown dwarfs failures. It makes them outcomes, valid ones, stable ones, final ones. The universe is not obligated to turn every accumulation of matter into something luminous or influential. It allows things to exist without justification. And in doing so, it exposes a deeper truth. That complexity is rare not because the universe resists it, but because the conditions required are precise. Narrow windows exist where transformation becomes possible. Outside those windows, existence continues in quieter forms. Brown dwarfs are the physical expression of that reality. They are what happens when the universe approaches a threshold and stops just short of crossing it. They remind you that becoming is conditional, that destiny is not written broadly but narrowly, that most of what forms does not shine, does not explode, does not matter in obvious ways, and yet it exists all the same. Stars are not born in moments of clarity or design. They converge from disorder, from regions of space that look empty and uneventful until you understand what you're actually seeing. Vast stretches of darkness in the galaxy are not voids at all. They are crowded with material so diffuse, so cold, and so spread out that it escapes ordinary perception. These are molecular clouds, the raw reservoirs from which stars eventually form. A molecular cloud is immense beyond intuition, hundreds of light years across, trillions of miles in every direction. And yet, inside this enormity, matter is astonishingly sparse. A few thousand atoms per cubic centimeter, less dense than the best vacuums humans can create. Nothing about such a place suggests inevitability or power. It looks static, inert, like a pause in the universe rather than a beginning. But gravity does not require density to act. It only requires mass and time. Within these clouds, small irregularities exist from the start. Slightly denser regions, minor fluctuations, turbulence from distant events, a shock wave from a long-forgotten supernova. The universe does not need intention to initiate change. It only needs imbalance. Once a region of a cloud becomes marginally denser than its surroundings, gravity begins to do what it always does. It pulls. At first, the collapse is slow, almost imperceptible. Gas drifts inward over hundreds of thousands of years. Nothing dramatic announces the transition. There is no clear line between before and after. But as matter falls inward, gravity strengthens. More mass collects. The inward pull grows. What began as a subtle preference becomes a directive. As the gas collapses, something counterintuitive happens. It heats up. Not because of fire or fusion, but because motion increases. Particles accelerate. Collisions become more frequent and more energetic. Temperature at its core is just motion. And collapsing matter moves faster. This heating is not optional. It is the unavoidable consequence of collapse. Gravity converts potential energy into kinetic energy, and kinetic energy expresses itself as heat. The cloud, once cold and dark, begins to glow faintly in wavelengths invisible to human eyes. A protostar is forming, though nothing that could reasonably be called a star exists yet. At this stage, gravity still rules absolutely. Fusion has not begun. There is no outward force to counter the inward pull. Matter continues to fall inward, feeding the growing core. Around it, a rotating disk of gas and dust forms, flattened by angular momentum. This disk will later become planets, asteroids, debris. But for now, it is simply excess material that could not fall straight in. The core grows hotter, denser, pressurizes. The environment becomes increasingly hostile to familiar structures. Molecules break apart. Atoms lose electrons. Matter transitions into plasma. None of this is directed. None of it is planned. It is simply what happens when gravity is allowed to operate uninterrupted. This phase can last millions of years, longer for smaller stars, shorter for massive ones. The process is patient, but relentless. Gravity does not hurry, but it does not stop. It tightens its grip gradually, ensuring that conditions grow more extreme with time. Eventually, a threshold is crossed. The core reaches temperatures of millions of degrees. Pressure becomes immense. Hydrogen nuclei, stripped of their electrons, move at tremendous speeds. Collisions become violent enough that occasionally two nuclei overcome their natural repulsion and fuse. At first, this happens rarely. A few reactions here and there. Insignificant compared to the overall collapse. But gravity does not tolerate partial solutions. As fusion begins, it releases energy. That energy creates outward pressure. At first, it is too weak to matter. But as temperature and density continue to rise, fusion accelerates. More reactions, more energy, more pressure pushing outward, and then, without fanfare, balance is achieved. The inward pull of gravity is finally matched by the outward pressure of fusion. Collapse halts. The protostar stabilizes. A star is born not in an explosion, but in equilibrium. A perfect sustained stalemate between forces that, individually, would destroy it. This balance is delicate beyond comprehension. If fusion increases slightly, the core heats and expands, lowering density and slowing reactions. If fusion slows, gravity tightens, heating the core and accelerating reactions. The star regulates itself automatically, without awareness or adjustment. Physics handles the bookkeeping. What matters here is inevitability. Once collapse begins, the outcome is largely determined. The mass of the original cloud fragment dictates how hot the core will become, how fast fusion will proceed, and what kind of star will result. A small fragment produces a small star. A large one produces a massive star. The difference between endurance and violence is decided long before ignition. Gravity is destiny in its purest form. There is no intervention, no redirection. A collapsing region cannot decide to become something else. It follows the path laid out by its initial conditions. The universe does not correct inefficiencies or optimize outcomes. It allows processes to unfold until they reach a stable configuration, or fail to do so. Star formation is not a creative act in the human sense. It is an emergent one. No single force builds a star. Gravity pulls, motion heats. Heat enables fusion. Fusion creates pressure. Pressure halts collapse. Each step follows logically from the one before it, without oversight or purpose. And this process does not happen once. It happens everywhere, continuously. Throughout galaxies, molecular clouds are collapsing, fragmenting, forming clusters of stars born from the same material at roughly the same time. Most stars are not solitary. They are siblings, sharing origins even as their futures diverge. Some of these newborn stars are massive and short-lived. Others are small and enduring. Some never fully ignite and become brown dwarfs. The diversity of outcomes arises naturally from variations in mass and environment. There is no quality control, only thresholds. This makes star formation feel both profound and indifferent. Profound because it gives rise to every source of light, heat, and complexity the universe knows. Indifferent because it proceeds without regard for what follows. Planets, life, chemistry, these are consequences, not goals. The universe does not form stars so that galaxies look beautiful or life can emerge. It forms stars because gravity collapses matter wherever conditions allow it. Everything else is downstream. Once a star ignites, it will spend most of its existence maintaining that balance, fusing hydrogen steadily, shining outward into space. But that long life is only possible because of the violence that preceded it. Without collapse, there is no ignition. Without heating, no fusion. Without fusion, no stability. Emergence requires imbalance. Structure requires pressure. Creation begins with collapse. When you look at a star, you are seeing the end result of a process that began in darkness, proceeded through compression and heat, and stabilized only when opposing catastrophes reached a temporary truce. That truce may last millions, billions, or trillions of years, but it is always conditional. Stars are not born because the universe wants light. They are born because gravity insists on consequence. And once gravity begins to act on sufficient mass, the path toward ignition becomes less a possibility and more a certainty. In that sense, star formation is not a miracle, it is a natural outcome. Given enough material and enough time, collapse is unavoidable. Heat follows. Fusion ignites. A star exists, not by design, by destiny written into the structure of space itself. A star looks permanent because it lasts longer than anything you're used to measuring. It shines steadily for millions or billions of years, unchanged within a human lifetime. That constancy creates the illusion of solidity, as if a star is a fixed object rather than an ongoing process. But this impression is deeply misleading. A star is not stable in the way a rock is stable. It is stable in the way a tightrope walker is stable, by continuously correcting forces that are trying to destroy it. At every moment of its existence, a star is balanced between two opposing catastrophes. Gravity is trying to crush it inward, compressing all its mass toward the center. Nuclear fusion is trying to blow it apart, releasing energy that pushes outward with tremendous force. Neither side ever rests, neither side ever weakens. The star exists only because these two pressures are matched with extraordinary precision. This balance is called hydrostatic equilibrium, but the name hides how precarious it truly is. There is nothing static about it. It is a constant negotiation, recalculated second by second. Gravity never stops pulling inward. Fusion never stops producing energy. The star survives only because the rates remain matched closely enough to prevent collapse or explosion. If gravity were even slightly stronger relative to fusion, the star would contract. Compression would increase temperature and pressure, accelerating fusion. If fusion were even slightly stronger, the star would expand. Expansion would cool the core, slowing fusion. This feedback loop is the only thing keeping the star intact. Stability is not a state. It is an ongoing correction. What makes this remarkable is the scale. The forces involved are immense beyond comprehension. The inward pressure at a star's core can be hundreds of billions of times greater than atmospheric pressure on Earth. The outward energy release converts millions of tons of mass into radiation every second. That these extremes cancel each other out so precisely is not a sign of gentleness. It is a sign of unforgiving precision. A star does not tolerate imbalance. There is no buffer zone where instability can linger harmlessly. Small deviations are corrected automatically and immediately. Large deviations end the star's current phase of existence. The margin for error is narrow, and the consequences of crossing it are absolute. This self-regulation gives stars their longevity. They can shine steadily for vast spans of time because they constantly adjust. When fusion speeds up, expansion cools the core. When fusion slows down, contraction heats it. The star behaves like a cosmic thermostat, maintaining conditions within a narrow range where fusion can continue without catastrophe. But this balance depends entirely on fuel. As long as hydrogen remains abundant in the core, fusion can continue at the rate required to oppose gravity. But fuel is not infinite. Every second of stability consumes it. The longer the star shines, the closer it moves toward a point where balance can no longer be maintained. This is where fragility enters the picture. A star's stability is conditional, not guaranteed. It lasts only as long as the internal reactions can generate enough pressure to counteract gravity. Once the primary fuel begins to run out, fusion slows. Outward pressure weakens. Gravity gains ground. At first, the changes are subtle. The core contracts slightly, temperature rises. Fusion shifts location or changes form. The star attempts to restore equilibrium by adjusting its internal structure. For a time, this works. The star survives by reorganizing itself, finding new ways to generate pressure, but each adjustment brings it closer to a threshold. Eventually, the core can no longer sustain the reactions needed to support itself. When that happens, gravity takes control completely. The balance that defined the star's life collapses. What follows depends on the star's mass, but the transition itself is always sudden. This reveals the truth behind stellar longevity. Stars do not endure because they are robust. They endure because they are delicately balanced and relentlessly regulated. Their long lives are not evidence of strength, but of precision maintained over immense spans of time. The universe does not reinforce this balance out of preference. It simply allows the feedback mechanisms to operate until they fail. There is no safety net. Once fusion can no longer compensate for gravity, collapse is inevitable. This understanding changes how you should think about stars. They are not solid objects radiating light. They are dynamic systems held together by an exact equality of opposing forces. They exist in a state that is always on the verge of becoming something else. Even small changes matter. A slight increase in mass can drastically shorten a star's stable lifetime by increasing core pressure and fusion rates. A slight decrease can extend that lifetime by orders of magnitude. Scale alters balance, and balance determines fate. This is why stellar evolution is so predictable. Not because stars follow a plan, but because the conditions for equilibrium are narrow, and the consequences of leaving them are unavoidable. Once the balance tips, there is no ambiguity about what happens next. There is something humbling about this. The universe allows stars to shine steadily for billions of years, but only by enforcing rules that are mercilessly strict. Stability is earned continuously, not granted. Every second of light represents a successful negotiation between collapse and explosion. When you look at a star, you are seeing a momentary outcome of this negotiation. You are seeing gravity and fusion locked in a stalemate that will not last forever. The light reaching your eyes is evidence that for now the balance holds, but it will not hold indefinitely. This fragility is not a flaw. It is a feature of a universe governed by thresholds rather than guarantees. Nothing complex exists without tension. Nothing stable exists without constant regulation. Stars are simply large enough to make this truth visible. Their steadiness is deceptive. It hides the fact that they are always one imbalance away from transformation. That their existence is defined not by permanence, but by duration. Not even the most reliable lights in the sky are temporary arrangements of force. Respect for stars does not come from imagining them as eternal. It comes from understanding how much must go right, continuously, for them to exist at all. How narrow the window is, how precise the balance must be. Hydrostatic equilibrium is not calm. It is restraint enforced by physics. It is the universe allowing something to shine only as long as it can justify its existence through perfect balance. And when that balance fails, the star does not weaken gradually. It changes state. The life it lived under equilibrium ends, and something new begins. Every star you see is balanced on that edge right now. Every star's life is defined by a single fuel. Hydrogen is not just what a star burns. It is what allows the star to exist at all. As long as hydrogen fusion continues in the core, gravity is held at bay, equilibrium is maintained, and the star remains stable. This phase lasts longer than any other, stretching across most of a star's lifetime, and from the outside it looks unchanging. But hidden beneath that apparent permanence is a clock that never stops counting down. Hydrogen does not replenish itself. Every fusion reaction consumes it. Every second of light subtracts from a finite supply. The star does not feel this loss in any conscious sense, but the physics registers it relentlessly. Over time, the composition of the core changes. Hydrogen becomes scarcer. Helium accumulates. And with that quiet shift, the conditions that once sustained balance begin to erode. At first, nothing seems different. The star shines as it always has. Fusion continues, gravity is resisted. But the core is no longer what it once was. As hydrogen is depleted, fusion slows. With less energy being produced, outward pressure weakens. Gravity, which has been waiting patiently since the star's birth, begins to gain ground. This is the turning point. Not a sudden event, not an explosion, but a loss of support. The core responds by contracting. Gravity compresses it inward, raising temperature and pressure. This contraction is not optional. It is the natural consequence of imbalance. As the core shrinks, it heats up, attempting to compensate for the slowing fusion. For a time, this works. The star adjusts, just as it has done countless times before. But the adjustment marks a fundamental change. The era of effortless stability is over. The star has entered the beginning of its end. From this point forward, the star's life is no longer defined by equilibrium, but by a series of responses to fuel exhaustion. Hydrogen fusion in the core ceases entirely once the supply is depleted. The core becomes inert, no longer producing energy. All that remains there is mass, compressed and unsupported, growing denser by the moment. Fusion does not stop everywhere at once. In many stars, hydrogen continues to fuse in a shell surrounding the core, where temperatures are still high enough. This shell produces energy, sometimes more than the core ever did. The star swells. Its outer layers expand. From the outside, the star may appear brighter, larger, more impressive than before. But this brightness is deceptive. It is not a sign of renewed vitality. It is a sign of instability. The core, now composed mostly of helium, continues to contract. Pressure rises. Temperature climbs. The star is burning time faster now, not slower. Each adjustment buys stability at the cost of accelerating what comes next. The clock that was once slow and almost irrelevant begins to tick audibly, at least. In cosmic terms, gravity has not changed. It has only waited. Eventually, the core reaches temperatures high enough to ignite new forms of fusion. Depending on the star's mass, helium may begin to fuse. Later, heavier elements may follow. Each new stage provides a temporary reprieve, a new source of outward pressure. But none of these stages last as long as the hydrogen phase. Each successive fuel burns faster, releases less energy, and supports the star for a shorter time. This sequence gives stellar death its sense of inevitability. Once hydrogen is gone from the core, there is no returning to the star's original state. The most stable, longest-lasting phase is over. Everything that follows happens on borrowed time. The pace of change accelerates. Where the hydrogen burning phase might last billions of years, helium burning may last millions. Later stages may persist for only thousands, years, or even days in the most massive stars. Each transition brings the star closer to a final imbalance that cannot be corrected. This is why running out of hydrogen matters more than any other event in a star's life. It is the moment when permanence gives way to process. When the star stops maintaining balance effortlessly and begins actively fighting gravity with diminishing resources. From this point on, collapse is not a possibility. It is a trajectory. The star does not collapse immediately. It resists. It reorganizes. It finds new ways to generate pressure. But every solution is temporary, and every temporary solution accelerates fuel consumption. The universe does not offer extensions without cost. There is something starkly mechanical about this. No drama, no pause, no hesitation. The laws of physics do not care that the star has been shining for billions of years. They do not preserve stability out of respect for duration. When fuel runs low, conditions change. When conditions change, outcomes follow. This is the countdown phase of stellar life. Not because time itself speeds up, but because options narrow. The star moves through a sequence of increasingly constrained states, each one closer to a point of no return. From the outside, this process can look like growth. The star may become a giant, swelling to enormous size, shedding material, glowing with a new color. But internally, The situation is worsening. The core is contracting faster. Gravity is tightening its grip. Fusion is becoming harder to sustain. Eventually, the star reaches a final threshold dictated by its mass. For smaller stars, this may result in a gentle shedding of outer layers and the exposure of a dense core. For massive stars, it leads to catastrophic collapse. But regardless of the outcome, the decisive moment always traces back to the same cause. The hydrogen ran out. This is not failure. It is completion. The star has done what it was always going to do. It converted mass into energy for as long as it could under the conditions it was given. Once that process reached its limit, the structure built on it could no longer be supported. The beginning of the end is quiet. There is no universal signal announcing it. No visible marker that says, "This star is dying now." The sky does not change suddenly. The light continues to arrive as it always has, delayed by distance and time. But inside the star, the narrative has shifted irrevocably. From this point forward, every change moves in one direction: toward collapse, toward transformation, toward an ending that was always implicit in the beginning. This is what gives stellar life its shape. Long stability followed by rapid change. Extended equilibrium followed by compressed transitions. The universe allows stars to shine for extraordinary spans of time, but when the conditions that made that shine possible are exhausted, the response is swift and uncompromising. The star's history narrows. Its future becomes specific. What comes next may be spectacular or subtle, violent or quiet, but the outcome is no longer in question. The loss of hydrogen support has set the final sequence in motion. Every star you see has either passed this turning point or is moving toward it. Some are still deep in their long, stable phase. Others are already reorganizing internally, though you cannot tell from their light. A few have already ended, their final moments still traveling toward you across space. This makes the night sky a collection of different countdowns at different stages. Some clocks are barely ticking, others are nearing zero. You cannot tell which by looking. The universe does not label its objects by age or urgency. But the rule is universal. No star escapes this transition. No matter how massive or how small, no matter how bright or how faint, the hydrogen will run out. When it does, the life the star has been living will end. And everything that follows flows from that single fact. The beginning of the end is not dramatic. It is decisive. Not every ending in the universe arrives with violence. Some come quietly, stretched out over time, unfolding with a kind of restrained inevitability that feels almost gentle by comparison. For many stars, the final chapters of their lives are not defined by explosions or collapse into exotic remnants, but by expansion, release, and gradual fading. These endings do not announce themselves with force. They simply happen step by step until the star is no longer what it once was. When a star like the Sun exhausts hydrogen in its core, it does not immediately tear itself apart. Instead, the loss of central fusion causes the core to contract and heat, while the outer layers respond in the opposite way. They expand. The star grows enormous, swelling far beyond its original size. This is the red giant phase, a transformation that looks dramatic but unfolds slowly. Over millions of years. As a red giant, the star becomes vast and diffuse. Its surface cools even as its total brightness increases. The light it emits shifts toward redder wavelengths, giving these stars their name. From the outside, a red giant appears majestic, luminous, almost serene. But this expansion is not a sign of strength. It is a response to imbalance. The star is rearranging itself in an attempt to remain stable under changing internal conditions. For any planets orbiting nearby, this expansion is catastrophic. Orbits are disrupted. Inner worlds may be engulfed entirely, vaporized within the star's extended atmosphere. The star does not notice. There is no malice in this process, no intent. It is simply the consequence of scale changing under pressure. Eventually, the red giant reaches a point where it can no longer hold on to its outer layers. The gravitational grip weakens as mass is lost through stellar winds. Shells of gas peel away, drifting outward into space. These layers carry with them the elements forged during the star's lifetime, released gently rather than hurled outward in violence. What remains behind is no longer capable of sustaining itself as a full star. The ejected material expands into space, forming a planetary nebula. Despite the name, these structures have nothing to do with planets. They are vast, glowing shells of gas illuminated by the hot core left behind. Their shapes can be intricate and delicate, shaped by subtle forces, magnetic fields, and slow asymmetries in the star's mass loss. Planetary nebulae are among the most beautiful objects in the universe. They look intentional, almost artistic, like cosmic sculptures suspended in space, but this beauty is temporary. These glowing shells disperse over tens of thousands of years, thinning out until they merge with the surrounding interstellar medium. The light fades. The structure dissolves. What looked permanent becomes diffuse. An anonymous dot at the center of this expanding nebula sits the star's remnant. A white dwarf. A white dwarf is not a star in the traditional sense. Fusion has ceased. There is no longer a source of energy being generated in the core. What remains is a dense, compact object supported not by fusion, but by quantum mechanical pressure. It is the exposed core of the original star, compressed into a volume not much larger than a planet. This object is extraordinarily dense. A single teaspoon of its material would outweigh mountains. And yet, despite this density, it is quiet. It does not collapse further because the laws of physics impose a limit on how tightly matter can be packed under these conditions. The white dwarf simply exists, hot at first, then gradually cooling. There is no explosion at this stage, no final flash. The star's light does not end abruptly. It diminishes slowly over billions of years as the white dwarf radiates away its remaining heat. The process is so gradual that the universe itself may change dramatically while the remnant cools. This kind of ending carries a different emotional weight. It is not shocking. It does not command attention. It feels more like exhaustion than defeat. The star has done what it could under the conditions it was given. Once its fuel was spent and its structure rearranged, it settled into a state that requires no further transformation. There is a melancholy to this quiet persistence. The white dwarf contains the memory of a star that once shone brightly, warmed surrounding space, perhaps hosted planets and systems that depended on its light. Now it remains as a compact, cooling ember, a physical record of what once was. And yet, there's beauty here too. The material released during the red giant phase enriches space gently, contributing to future generations of stars and planets. The planetary nebula, though short-lived, spreads heavy elements without the violence of a supernova. The universe is changed but not shocked. This contrast matters. It shows that transformation does not always require destruction, that endings can be productive without being catastrophic. The universe allows some stars to bow out softly, returning their material without tearing space apart in the process. Acceptance is built into this path. The star does not fight collapse until it explodes. It adjusts, expands, releases, and finally settles. Each stage follows logically from the one before it. There is no abrupt failure, only a gradual transition from one form of existence to another. Compared to the violent deaths of massive stars, these quiet endings feel almost intimate. They unfold slowly enough that the universe barely seems to notice. But over time, their cumulative effect is profound. Most of the elements that make rocky planets and complex chemistry possible are released through these gentle processes, not through explosions. The white dwarf will persist for unimaginable spans of time, slowly cooling toward darkness. It will not collapse further. It will not reignite. It will simply fade, becoming dimmer and colder as the universe expands around. Its story ends not with an event, but with a gradual absence. This kind of ending reframes what it means for something to be finished. The star is not erased. It is transformed into a quieter state, one that no longer demands energy or balance. The tension that defined its life is gone. What remains is stability of a different kind. Red giants, planetary nebulae, and white dwarfs form a sequence that feels almost reflective. Expansion, release, rest. There is no urgency here. No spectacle meant to be witnessed. Just a slow unwinding of structure that once required constant effort to maintain. In these endings, the universe shows a softer side without becoming kind. There is no mercy involved, only physics allowing outcomes that do not require violence. Balance gives way to release. Fusion gives way to cooling. Activity gives way to persistence. When you look at images of planetary nebulae, glowing briefly against the dark, You are seeing a farewell that does not shout. When you consider white dwarfs, faint and dense, you are looking at what remains when all dramatic possibilities have been exhausted. Not every star dies loudly. Many simply let go. And in that quiet letting go, there is a different kind of beauty. A star can create only so much before it reaches a hard boundary written into the structure of matter itself. For most of its life, fusion is productive. Hydrogen becomes helium. Helium can become carbon and oxygen. In massive stars, fusion continues, building heavier and heavier elements in layered shells, each one forged under higher pressure and temperature than the last. It feels like progress, like the universe steadily assembling complexity from simplicity. But that progression stops abruptly at iron. Iron is not just another element. It is a dead end. Up to iron, fusion releases energy. Each fusion reaction produces slightly lighter nuclei than the ones that went in, and the missing mass becomes energy. That energy is what supports the star, what pushes outward against gravity, what allows the entire structure to exist. Fusion is not just manufacturing elements. It is paying the energy cost of stability. Iron breaks that contract. When atomic nuclei lighter than iron fuse, energy is released. When nuclei heavier than iron try to fuse, energy is required. The process reverses. Instead of generating pressure, fusion begins to drain it. Iron is the most tightly bound nucleus. It represents the lowest energy state matter can reach through fusion alone. Beyond it, fusion is no longer a source of support. It becomes a liability. This is why stars cannot simply fuse their way into creating everything. Once iron accumulates in the core of a massive star, the engine that held gravity back fails catastrophically. Fusion stops being helpful. Outward pressure collapses. Gravity, which has been waiting patiently through every stable phase, takes over completely. The star's core implodes. This collapse happens fast. In seconds, the core compresses to extreme densities. Protons and electrons are crushed together. Neutrons form. The structure that existed moments before is erased. What follows is not a gentle transition, but a violent reversal of everything the star has been doing for millions of years. And then, the rebound. The collapsing core slams into itself and stiffens. The enfolding outer layers crash down and are suddenly stopped. Energy floods outward in a shock wave that tears through the star. In that moment, conditions become so extreme that the normal rules governing matter loosen their grip. Temperatures reach billions of degrees. Neutrons and protons collide chaotically. Atomic nuclei are built and destroyed in rapid succession. This is supernova alchemy. In the heart of that explosion, elements heavier than iron are created. Gold, uranium, platinum, iodine, lead, elements that cannot be produced during a star's stable life are forged only in these brief, catastrophic moments. The energy required to build them does not come from fusion. It comes from collapse. Death becomes productive. Without this final violence, these elements simply would not exist. There is no alternative pathway. No slower, gentler process that can assemble them under normal stellar conditions. The universe requires a star to fail completely before it can create its heaviest materials. This is the revelation that reshapes how you should think about destruction. The supernova is not excess, it is necessity. Consider calcium, the element that makes your bones rigid. It is not a product of quiet fusion and long-lived stars like the Sun. It is produced in the later stages of massive stars and released into space only when those stars die. The iron in your blood follows the same rule. The gold that humanity has prized for millennia exists only because stars collapsed violently enough to synthesize it and disperse it into space. Uranium, the element that heats planets from within and makes nuclear reactions possible, can be traced to the same origin. It requires neutron-rich environments that exist only during catastrophic stellar death. Without supernova, the periodic table would be severely truncated. The universe would be chemically impoverished. This is why death matters. During a star's life, the elements it creates are locked inside it. They remain inaccessible, trapped under immense gravity. Fusion alone does not distribute complexity. It concentrates it. Only when a star's structure fails does that material escape. The supernova tears the star apart and flings its contents outward at incredible speeds. The shock wave carries newly forged elements across interstellar space, seething gas clouds that will eventually collapse into new stars and planets. Matter that was once locked inside a single object becomes part of the wider universe. Without this redistribution, creation would stall. The universe would be filled with stars made mostly of hydrogen and helium, shining steadily but incapable of giving rise to planets like Earth or chemistry like life depends on. Supernova are not optional events sprinkled into cosmic history for spectacle. They are the mechanism by which the universe escapes its own simplicity. There is no intention behind this, no foresight. The universe does not explode stars in order to make life possible. Life is a downstream consequence of a process that operates without regard for outcome, but the necessity remains. No collapse, no heavy elements. No heavy elements, no complexity. This is why iron marks such a profound boundary. It is the point where creation through stability ends and creation through destruction begins. The star cannot continue as it is. It cannot negotiate a new equilibrium. The only way forward is collapse, and collapse in this context is not failure. It is transition. When you understand this, the idea of a supernova shifts. It stops being a cosmic accident and becomes a structural requirement. The universe needs some stars to end violently in order to move beyond the elements that fusion alone can provide. Meaning emerges from necessity, not design. The atoms in your body tell this story whether you recognize it or not. Your bones contain calcium born in dying stars. Trace amounts of gold circulate through your blood. Iron binds oxygen in your cells. These elements were not created to serve you. They were created because physics allowed them to exist only under extreme conditions. And those conditions occurred. This reframes mortality itself at a cosmic level. The death of a star is not an erasure of value. It is a release of potential. The star's long life is what prepares the material. Its violent end is what makes that material available. Even the most catastrophic endings in the universe are not arbitrary. They happen where thresholds are crossed, where stability is no longer possible, and where collapse opens pathways that stability could never access. Supernova are brief. In seconds or days, they accomplish what billions of years of fusion cannot. They expand the chemical vocabulary of the universe. They ensure that future structures can be more complex than past ones. This is why the universe is layered with generations. Stars form from material enriched by earlier deaths. Each generation carries a more diverse set of elements than the last. Complexity accumulates not smoothly, but in pulses tied to destruction. The revelation is uncomfortable because it breaks a familiar association. We tend to separate creation from destruction, treating them as opposites. In the universe, they are partners. Stability builds up potential. Collapse releases it. Without both, progress halts. When you look at a piece of gold, you are holding the product of a star that could no longer support itself. When you feel the strength of your bones, you are experiencing matter that required a catastrophic ending to exist. The universe did not give these things gently. It tore itself apart to make them possible. Death matters because some things can be created only when systems fail completely. This is not poetic language. It is a physical rule. The universe advances not by preserving everything, but by allowing some structures to end decisively. Supernova alchemy is the proof. Without it, the universe would be simpler, emptier, and incapable of producing anything resembling the world. Stars do not die so that meaning can exist. Meaning exists because stars die. Once you see that, destruction stops looking like an interruption and starts looking like a requirement. There are places in the universe where familiar concepts stop working, where matter is compressed so intensely that the distinctions you rely on, solid, liquid, empty space, lose meaning. Neutron stars exist at that edge. They are what remains when a massive star collapses so completely that even atomic structure is no longer allowed to behave normally. Nothing about them fits comfortably inside human intuition. They are not large. They are not bright. But they are extreme in a way that destabilizes any ordinary sense of reality. A neutron star packs more mass than the sun into a sphere roughly the size of a city. That single fact should already feel wrong. Gravity has crushed matter to density so high that electrons and protons can no longer remain separate. They are forced together, forming neutrons, collapsing atomic space almost entirely. What was once a star becomes an object so dense that a single teaspoon of its material would outweigh mountains. This density is not an exaggeration, it is literal. Matter inside a neutron star is packed so tightly that there is almost no empty space left. The atoms that once made up the star are gone as independent entities. Their internal structures have been erased. The result is something closer to a giant atomic nucleus than anything you would recognize as matter. Gravity here is absolute. Escape velocity reaches a significant fraction of the speed of light. Space itself is warped sharply around the object. Time runs differently near its surface. If you could stand nearby an impossible thought experiment, you would experience gravity, so strong that your body would be stretched and torn apart at the molecular level. There is no survival at this scale. There is only compression, and yet, even gravity needs resistance. Neutron stars do not collapse indefinitely, at least not always. They are held up by a pressure that has nothing to do with heat or fusion. This support comes from the quantum rules governing particles themselves. Neutrons resist being packed arbitrarily close together. Not because of force in the classical sense, but because the laws of quantum mechanics forbid it. Reality itself imposes a limit. This is where physics becomes unfamiliar. The star is no longer supported by energy production. Fusion is long gone. What remains is a standoff between gravity and the fundamental rules of matter. If the mass is low enough, the neutron star stabilizes. If it is too high, even this resistance fails, and collapse continues toward a black hole. There is no gradual transition. Only thresholds. Among neutron stars, magnetars represent the most extreme expression of this state. Magnetar is a neutron star with a magnetic field so powerful that it defies comparison. Trillions of times stronger than Earth's magnetic field. Stronger than anything humans can produce or even meaningfully simulate. At these strengths, magnetism is no longer a subtle influence. It dominates the environment completely. A magnetar's magnetic field is so intense that it can distort atoms at a distance. It can strip electrons from matter without contact. It can crack the rigid crust of the star itself, producing starquakes that release more energy in a fraction of a second than the sun emits in hundreds of thousands of years. These outbursts are not explosions in the traditional sense. They are releases of stored magnetic energy, snapping back into new configurations when the field becomes too stressed to maintain its shape. The result is a flash of radiation so powerful it can affect space across the galaxy. If a magnetar were placed halfway across the moon's distance from Earth, its magnetic field would erase every credit card, wipe every hard drive, and disrupt electronic systems instantly. That is how concentrated its influence is. And yet, in cosmic terms, it is still a small object, barely noticeable in size. This mismatch between scale and power is what makes neutron stars so unsettling. They are not vast, they do not fill space. They concentrate extremity into a compact form, proving that reality does not require size to reach its limits. It only requires pressure. Inside a neutron star, matter exists in states that are still not fully understood. Theories predict exotic phases, superfluids, superconducting cores, particles behaving collectively rather than individually. At these densities, the distinction between particles blurs. The equations that describe everyday matter stop being reliable. Physics does not fail here, but it becomes incomplete. We can model neutron stars mathematically. We can infer their properties from observation, but we cannot recreate their conditions. There is no laboratory that can approach these pressures. These objects are natural experiments that push physical law into regimes, inaccessible by any other means. This is where reality feels fragile. The same laws that allow matter to exist in familiar forms also permit it to be compressed into something utterly alien. There is no safety margin built into the universe to preserve intuitive structure. If conditions demand it, atoms will collapse, forces will dominate. Rules will assert themselves without regard for comprehensibility. Magnetars take this further by adding instability to extremity. Their magnetic fields are not calm, they evolve, they twist. They fracture the star's crust. When that crust breaks, the release of energy is sudden and immense. Gamma rays flood space. Radiation spikes so sharply that detectors across the galaxy register the event. These flashes last fractions of a second. They are brief. But in that brief moment, the magnetar becomes one of the most energetic objects in the universe. Not because it is large, but because its internal stresses are so extreme that failure releases enormous power. There is something deeply destabilizing about this. The idea that matter can exist in such compressed states, that familiar forces can scale up so dramatically, that the universe allows conditions where intuition simply stops applying. Neutron stars are not transitional curiosities. They are stable endpoints for many massive stars. The universe produces them regularly. They are scattered throughout galaxies, spinning rapidly, emitting beams of radiation, warping space around them. They are reminders that the cosmos is not obligated to remain within comfortable bounds. What makes them even more unsettling is their precision. A neutron star balances on a knife edge between stability and collapse. Add a little mass, and it becomes a black hole. Remove some, and it might never have collapsed this far. The difference between radically different realities is measured in small fractions of solar mass. Again, thresholds dominate outcomes. Magnetars, in particular, live with constant tension. Their magnetic fields decay over time, releasing energy sporadically. Their crusts strain under forces no material could withstand on Earth. They are stable only in the sense that collapse is postponed, not avoided. This pushes the idea of endurance into a new category. Neutron stars endure not because they are gentle or balanced, but because they are locked into configurations where change is restricted by fundamental limits. They are prisons of force. At this edge, physics stops feeling like a set of tools and starts feeling like a boundary. There are places the universe can go and places it cannot. Neutron stars sit exactly at one of those boundaries, showing how far matter can be pushed before identity itself breaks down. They challenge the idea that reality is smooth or continuous. They reveal that under enough pressure, new regimes appear abruptly. Familiar behavior disappears. New rules take over. Extreme awe comes not from size here, but from concentration. From knowing that within a region smaller than a city, forces exist that can outshine stars, warp time, and fracture space's assumptions. From knowing that the universe permits such configurations casually as byproducts of stellar death. Neutron stars are not warnings. They are demonstrations. Proof that the universe has no obligation to remain intelligible at every scale. That the same laws governing your body can also govern matter crushed beyond recognition. When physics breaks down in your understanding, it does not mean the universe has failed. It means you have reached a boundary where intuition no longer applies. Magnetars and neutron stars live there permanently. They are what happens when gravity is allowed to finish its work without interruption. When collapse is halted only by the most fundamental constraints reality has to offer. When matter is stripped of every comfort and forced into its most extreme possible state. Short of disappearance. They do not exist to be understood easily. They exist because the universe permits them, and in their existence, they show you how close reality always is to becoming something entirely unrecognizable. There is a point beyond which mass no longer builds structure. It erases it. Black holes represent that point. They are not objects in the ordinary sense, not stars, not remnants you can point to and say, this is what remains. They are what happens when mass overwhelms every known form of resistance, when gravity is allowed to complete its work without compromise. At that boundary, reality does not just change. It becomes inaccessible. A black hole forms when collapse is no longer stoppable. In massive stars, once all possible forms of pressure have failed, fusion pressure, electron pressure, neutron pressure, gravity faces no opposition. The core falls inward endlessly, compressing mass into a region so small and dense that the equations describing space and time themselves begin to fail. What remains is not a surface, but a boundary. That boundary is the event horizon. The event horizon is not something you can touch or stand on. It is a limit written into space-time. Cross it, and no signal of any kind can return. Not light. Not matter, not information. The universe draws a line and says, beyond this point, causality no longer connects to the outside. This is what makes black holes fundamentally different from every other object. Discussed so far. Neutron stars push matter to extremes, but they remain observable. They emit light. They spin. They interact. Black holes do not reveal their interiors at all. Everything we know about them comes from how they affect their surroundings, never from what happens inside. Approaching a black hole distorts reality in ways that feel deeply wrong. Time slows relative to distant observers. The closer you get to the event horizon, the more extreme the distortion becomes. To an outside observer, anything falling toward a black hole appears to slow down, stretch, and fade, never quite crossing the horizon at all. The fall seems to freeze. From the perspective of the falling object, the experience is entirely different. Time feels normal. There is no warning light, no cosmic alarm. The event horizon is not marked by fire or force. It is crossed without ceremony. One moment you are outside, the next you are not. And once crossed, all possible futures point inward. This mismatch between perspectives is not illusion. It is physics. Time itself behaves differently depending on where you are relative to extreme gravity. There is no single, universal clock that governs reality near a black hole. Each path through spacetime experiences its own version of duration. Inside the event horizon, the concept of later loses its meaning in the way you expect. The singularity, the point where mass is compressed beyond known limits, is not just a place in space. It is a moment in time. Once inside, reaching the singularity is as inevitable as reaching tomorrow. You cannot avoid it any more than you can choose to stop time. This inevitability is unsettling because it strips away agency. Outside the black hole, objects move through space toward destinations. Inside, all possible paths lead to the same end. Choice disappears. Direction collapses into certainty, and yet, the singularity itself is unknowable. Our equations predict infinite density and zero volume. But infinities are signals that a theory has reached its breaking point. Physics does not like infinities. They suggest missing understanding, not literal conditions. Somewhere inside a black hole, the rules we rely on stop working, and no observation can guide us past that point. This is where unknown physics dominates. We do not know what actually exists at the center of a black hole. We do not know how matter behaves there, or whether the concept of matter even applies. We do not know whether information is destroyed, transformed, or preserved in ways we cannot yet describe. The black hole forces humility because it marks a region where certainty ends. Event horizons are cosmic censorship. They hide failure modes of our understanding behind boundaries we cannot cross. The universe allows black holes to exist, but it does not allow us to look inside them. They are limits placed not on travel alone, but on knowledge. This is why black holes inspire a unique blend of fear and awe. They are not violent in the explosive sense. They do not tear space apart visibly. They simply remove things from the universe of interaction. Once something crosses the horizon, it is gone from the story you can observe. Mass has ultimate authority here. Not energy, not pressure, not motion. Mass curves spacetime so severely that paths which once led outward now curve back inward. Light itself bends. Escape becomes impossible, not because of force but because of geometry. This is difficult to grasp because we are used to thinking of gravity as a pull. Near a black hole, gravity is not pulling objects inward through space. It is reshaping space so that inward is the only remaining direction. Black holes also distort time far from their centers. Clocks near them tick differently. Process is slow. Causality stretches. The universe becomes asynchronous in extreme ways. A black hole is not just a place where things disappear. It is a region where the ordering of events itself becomes relative, and yet black holes are common. They are not rare accidents. Most large galaxies harbor supermassive black holes at their centers, millions or billions of times more massive than the Sun. These objects shape galactic evolution, regulate star formation, and anchor cosmic structure. The universe does not avoid its own extremes. It builds around them. Supermassive black holes are quieter than their smaller cousins. Their event horizons are vast. Their tidal forces at the edge are relatively gentle. You could, in principle, cross the horizon of a very large black hole without immediate destruction. This makes the idea even more unsettling. There is no dramatic threshold, just a point beyond which return is impossible. This quietness reinforces the mystery. Black holes do not announce themselves as monsters. They reveal themselves indirectly through the motion of stars, the glow of accreting matter, the bending of light. They exist as absences more than presences. They are defined by what cannot escape, the ultimate consequence of mass. Then is not explosion or brilliance. It is silence. A region where cause and effect are severed from the rest of the universe. Where information flow ends. Where the future collapses into a single outcome. This forces a profound humility. The same laws that allow stars to shine and planets to form also allow regions of spacetime to become permanently inaccessible. The universe does not guarantee transparency. It does not promise that everything can be understood or observed. Black holes are not errors. They are valid solutions to the equations governing reality. That fact alone should be unsettling. It means the universe permits states where knowledge is fundamentally limited, not just practically difficult. When you consider black holes, scale becomes secondary. What matters is inevitability. Once mass passes a certain threshold within a given volume, collapse cannot be prevented. The outcome is not negotiable. Pressure fails. Forces saturate. Geometry takes over. This makes black holes the final punctuation mark in the story of stars. Not an ending that resolves neatly, but one that closes off entire chapters permanently. What enters does not come back. What happens inside does not inform the outside, and yet, black holes do not end the universe's story. They coexist with it. Matter falls in, energy radiates outward. Space continues to expand. Galaxies evolve around these dark centers, indifferent to the fact that something unknowable sits at their core. Fear arises not because black holes threaten you personally, but because they reveal a truth about reality. That there are places where understanding stops. That not everything is recoverable. That mass, given the chance, can rewrite the rules of engagement entirely. Awe arises from the same realization. The universe is not constrained to remain simple or accessible. It is capable of building regions where space and time behave in ways no mind evolved for survival could intuit. Black holes are not just objects. They are boundaries. They mark the edge of explanation. They show you what happens when mass is allowed to win completely, and in doing so, they remind you that the universe is larger, stranger, and less obligated to make sense than anything you will ever experience directly. Beyond the event horizon, reality continues. You just don't get to follow it there. Nothing in the universe is ever truly discarded. Even the most violent endings do not remove material from existence. They redistribute it. When stars die, whether quietly or catastrophically, their substance does not vanish. It spreads. It mixes. It becomes available again. This is how the universe closes its loops, not through renewal in a moral sense, but through conservation enforced by physics. Every star begins with material that has already lived other lives. Hydrogen and helium formed in the earliest moments. After the universe began, heavier elements were added later, forged inside stars that no longer exist. When a new star ignites, it does so from matter that has been processed, expelled, and recycled countless times before. Birth is never a first event. It is always a continuation. Star death is the mechanism that makes this circulation possible. During a star's life, gravity traps material tightly. Fusion builds new elements but keeps them locked away. Without an ending, that material would remain inaccessible, sequestered inside long-lived objects. The universe would stagnate chemically. Complexity would plateau. Death is what releases the inventory. When a star sheds its outer layers or explodes, as a supernova, it returns matter to space in a usable form. Gas clouds become enriched with elements that did not exist before. Carbon, oxygen, silicon, calcium, iron. Each death adds new possibilities to the environment it leaves behind. Space is not empty between stars. It is filled with residue, layered with history. Over time, this enriched material drifts, mixes, cools. Shock waves from explosions compress it. Gravity pulls it together again. Molecular clouds form from the remains of previous generations. Within them, collapse begins anew. New stars ignite, built from the ashes of old ones. This is not rebirth in a poetic sense. There is no memory carried forward. No intention. Just continuity. The same atoms cycle through radically different roles. An iron atom forged in a supernova may drift through space for millions of years, become part of a gas cloud, collapse into a new star, then later be incorporated into a planet. It may spend time locked in rock, dissolve into oceans, pass through living systems, and eventually return to space again. The universe does not label phases. It allows transitions. This circulation reveals the universe as a closed system in practice, if not in totality. Matter is conserved. Energy changes form. Nothing essential is lost. What looks like an ending at one scale is simply a redistribution at another. Stars are the engines of this circulation. They concentrate matter, transform it, and then disperse it. Without stars, the universe would be chemically simple and largely inert. Without star death, it would become chemically static. Both creation and destruction are required to keep the system dynamic. This perspective changes how scale feels. Individual. Stars are temporary. Entire galaxies evolve. But the material itself persists, moving through cycles far longer than any single structure. The universe does not need permanence at the level of objects. It achieves continuity at the level of process. There is comfort in this, though it is not sentimental. It does not promise preservation of form. It promises persistence of substance. What exists now will not exist forever in this configuration, but its components will continue. They will participate in future arrangements governed by the same rules. Even black holes do not fully break this loop. Though they remove matter from direct interaction, they are not sinks that erase material from the universe entirely. They grow by accretion, shape their surroundings, and influence star formation on galactic scales. Their presence alters flows, rather than terminating them. Even here, continuity dominates. Over cosmic timescales, galaxies become recycling systems. Stars form, live, and die within them. Material moves outward, inward, mixes, settles. Regions of space change composition gradually. The universe enriches itself incrementally, generation by generation, without plan or endpoint. This is systems thinking at its most expansive. No single star matters on its own. Its significance lies in how it contributes to flows larger than itself. Each life alters the probabilities of what comes next. Each death expands the range of possible futures. The comfort here comes from inevitability, rather than reassurance. The universe does not risk running out of material. It does not depend on perfect outcomes. It tolerates waste, inefficiency, failure, and loss because nothing is truly removed from circulation. The system absorbs everything, even time participates in this loop. Past events shape present conditions. Present structures become future resources. The night sky is not a static display of independent lights. It is a snapshot of different stages within a single, ongoing process. When you look at a region where stars are forming, you are seeing the universe reuse itself. When you look at a supernova remnant, you are seeing the raw input for future stars. When you look at a quiet, mature star, you are seeing a temporary storage phase in a longer cycle. This continuity dissolves sharp distinctions between beginning and end. Birth and death are not opposites. They are adjacent phases. One flows into the other automatically, without pause or interpretation. The universe does not mourn stars that die. It incorporates them. Their material becomes part of a larger reservoir that will eventually condense again. Loss at one scale is availability at another. This is why the universe does not trend toward emptiness in a simple way. Even as it expands and cools, processes continue, matter rearranges, energy redistributes. Stars form less frequently over time, but they do not stop suddenly. The system winds down gradually, stretching its activity across unimaginable durations. Understanding this loop reframes endings. A star's death is not the disappearance of something unique and irreplaceable. It is the release of a configuration that has served its role. The universe is not sentimental about structure. It is committed to continuity of process. This does not erase individuality. Each star's life is still distinct, shaped by mass and environment. But individuality exists within a framework that prioritizes circulation over preservation. What matters is not that a particular star continues, but that the system remains capable of producing stars at all. Comfort emerges from that scale shift. Not because anything is protected, but because nothing is wasted. The universe does not accumulate dead ends. It accumulates resources. Even the most extreme events, supernova, neutron star mergers, serve this circulation. They inject energy and material back into space, preventing stagnation. They reset conditions. They ensure that collapse can happen again elsewhere. The universe closes its loop not by returning to an earlier state, but by reusing components under new conditions. Each cycle is different. Each generation of stars is slightly richer in heavy elements than the last. Complexity ratchets upward, unevenly, punctuated by destruction. This is not progress in a moral sense. It is progression in a physical one. The system explores what is possible given its rules, without regard for outcome. Seeing the universe this way can be stabilizing. It removes the need for permanence. It replaces it with participation. Everything that exists now is part of a flow that existed before it and will continue after it. There is no final arrangement to protect or preserve. The night sky becomes a map of circulation rather than a collection of isolated lights. Each star is both a product of past deaths and a contributor to future ones. The boundaries blur. History and potential coexist. The universe does not start over. It moves forward by reusing what it already has. That reuse is not efficient or gentle. It is thorough. When stars die, they do not take their contributions with them. They distribute them. When new stars form, they do not invent material. They inherit it. The loop remains unbroken. Continuity, then, is not about survival of form. It is about the persistence of matter and process across time. The universe remains active not because nothing ends, but because endings feed beginnings. In that sense, the cosmos is not fragile. Individual structures are. Systems are not. This perspective offers a different kind of comfort. Not the promise that things will last, but the assurance that they will matter beyond their duration. Not because the universe assigns meaning, but because it enforces reuse. Nothing is isolated. Nothing is final. Everything participates. The cosmic loop closes. Not with resolution, but with continuity. Everything you followed outward through the universe eventually folds back into you. Not symbolically, not metaphorically. Physically. The same processes that build stars, break them apart, and recycle their remains do not stop at planets or galaxies. They continue uninterrupted into bodies, into cells, into breath. The distance between cosmic scale and personal scale is smaller than it feels, because the boundary was never real. The calcium in your bones did not originate with you. It did not originate with Earth. It was forged under pressures so extreme that no biological structure could survive them. Long before bones were possible, calcium existed as raw material inside stars that no longer exist. Those stars built it in their cores and released it only when they could no longer hold themselves together. Your skeleton is assembled from the remains of stellar failure. Your blood carries the same history. Iron atoms move through your bloodstream, binding oxygen, enabling metabolism, sustaining life moment by moment. Those iron atoms were not designed for this role. They were not made with blood in mind. They were formed in massive stars, accumulated until fusion could no longer continue, and then expelled violently into space. Only after drifting through the galaxy, mixing into clouds, forming planets, and cycling through countless non-living configurations did they become part of you. Even your breath is not exempt. The oxygen you inhale was produced inside stars that expanded and shed their outer layers long before Earth existed. Photosynthesis merely borrowed it from a planetary reservoir that was already enriched by stellar deaths. Every breath is a continuation of a chemical process that began far from here, under conditions nothing alive could endure. There is no part of you that is original to this moment. Atoms do not recognize identity. They move through forms without attachment. An atom of carbon may spend time inside a star, then in interstellar space, then in a rock, then in a leaf, then in a body, then in the air again. At no point does it change its fundamental nature. It is rearranged, reassigned, repurposed. Meaning is imposed by context, not carried by the atom itself. This reframes what identity actually is. You are not a collection of special materials. You are a temporary configuration of ordinary ones. The distinction that feels profound from the inside dissolves when viewed from the scale where atoms operate. Nothing in you belongs to you in a permanent sense. Everything you are is borrowed, briefly organized, then eventually released. This is not a diminishing realization. It is an honest one. The atoms in your body have passed through multiple stars. Not all of them, not in neat succession, but many. Some were forged in the first generations of stars after the universe cooled enough to allow structure. Others were created later, in more violent events. Over billions of years they mixed, scattered, recombined, and eventually became part of a planet where chemistry could persist long enough for life to arise. You are downstream of all of that. The universe does not distinguish between living and non-living matter at the level of physics. The same rules govern both. The difference is not substance but arrangement. Life is not made of special atoms. It is made of familiar atoms held in unstable patterns that require constant energy to maintain. That instability is essential. Your body is not static. It is a flow. Atoms enter and leave continuously. You replace much of yourself over time through eating, breathing, shedding, metabolizing. The boundary you perceive as you is porous and temporary. It persists only as long as the pattern holds. When that pattern breaks, the atoms do not vanish. They disperse. They return to circulation. This is the same logic that governs stars. A star is not its material. It is a phase matter passes through under certain conditions. When those conditions fail, the star ends, but the matter continues. The difference between a star and a body is scale, not principle. Seeing this collapses the distance between cosmic events and personal existence. The supernova that created the iron in your blood is not an abstract past, it is a prerequisite. Without that collapse, your body could not function. Without stellar death, there is no breath, no bone, no circulation. Identity, then, is not something embedded in matter. It is something that emerges when matter is arranged in a particular way for a limited time. You are not separate from the universe. You are one of its configurations, as temporary and as legitimate as any other. This can feel destabilizing at first. The idea that nothing about you is permanent, that your substance has lived other lives and will live others again, challenges the intuition that identity must be fixed to be meaningful. But meaning does not require permanence. It requires participation. You are participating in a process that began long before you and will continue long after. Your body is one moment where the universe became self-aware enough to reflect on its own material. That awareness does not elevate the atoms themselves. It adds a layer of experience to their ongoing movement. When you move, when you breathe, when your heart beats, you are not acting in isolation. You are continuing motions that began under gravity, pressure, fusion, and collapse. The same physics that shaped galaxies now governs the chemistry in your cells. There is no break in the chain. This intimacy with the universe is not poetic invention. It is mechanical truth. The carbon atoms that form complex molecules in your brain were assembled through stellar processes that had nothing to do with thought. And yet here they are, arranged in ways that allow reflection, memory, and perception. The universe did not plan this outcome, but it permits it. And that permission is enough. Understanding this shifts identity away from ownership and toward alignment. You do not own your atoms. You host them, briefly. They pass through you the way they pass through everything else. What makes you distinct is not what you are made of, but how long and how coherently the arrangement holds. This also reframes loss. When bodies end, when patterns dissolve, nothing essential is destroyed at the level the universe operates on. The atoms return to circulation, carrying no trace of the identity they once supported, but retaining all their physical potential. What mattered about the pattern mattered while it existed. Its end does not negate its reality. Stars are not diminished by dying. Bodies are not diminished by ending. Both are phases in a system that prioritizes flow over preservation. There is intimacy in recognizing that your bones were once part of stars, that your blood carries the residue of explosions, that your breath cycles elements older than the planet. Beneath your feet, it collapses abstraction into embodiment. The universe is not out there. It is assembled into you. And yet, this does not make you central. It makes you connected. You are not the goal of these processes. You are one of their outcomes. A temporary one. A fragile one, but no less real for that. The universe is not made meaningful by you. You are made possible by it. This humility does not erase significance, it relocates it. Meaning does not come from being permanent or unique at the level of substance. It comes from being a moment where matter was arranged in a way that allowed experience to occur. When you look at the night sky, you are not looking at something separate from yourself. You are looking at other configurations of the same material, operating at different scales, under different pressures, at different stages of the same circulation. Some are bright, some are dead, some are forming. You are another phase among them. The loop that stars participate in does not end at planets. It passes through ecosystems, through bodies, through consciousness, and back into the environment. The distinction between cosmic and personal collapses when you follow the atoms closely enough. Your identity is real, but it is not permanent. It is not owned, it is not isolated. It is a temporary arrangement that exists because the universe allows matter to be rearranged in complex ways for brief periods of time. That does not make it small. It makes it precise. You are made of dead stars, yes. But more accurately, you are made of material that has never stopped changing form. Stars were one phase, bodies are another. Neither is final. Neither is separate. The universe did not stop when it formed stars. It did not stop when planets formed. It did not stop when life emerged. It continues through you without pause, without intention, without needing permission. Identity at this scale is not something you possess. It is something you temporarily enact. And when that enactment ends, nothing collapses into nothingness. The atoms move on. The loop remains intact. Everything you followed outward has folded back inward. Not as metaphor, dot as matter, dot at the end of all this distance, all this scale, all this outward expansion of thought. There is a simple realization waiting quietly underneath it all. You were never separate from what you were looking at. The separation only felt real because of scale, because of habit, because of the way perception narrows when it stays close to itself. But nothing you traced through the universe exists outside the same system that assembled you. There is no clean boundary where the universe stops and you begin. The atoms in your body obey the same laws as the atoms in stars. The forces shaping galaxies also govern the chemistry in your cells. Gravity does not switch rules when it encounters life. Time does not slow down out of respect for meaning. Everything that applies out there applies here without exception. The universe does not make special cases, and yet here you are. This is not contradiction. It is consequence. You are not an observer standing apart from the cosmos, watching it unfold. You are one of its outcomes. A temporary configuration where matter became complex enough to sense, reflect, and ask questions about its own origin. The universe is not something you look at. It is something you are doing. This does not make you important in a grand central sense. It makes you connected in a deep structural one. When you think, when you feel, when you experience awe or fear, or peace, those are not intrusions into an otherwise mechanical universe. They are expressions of it. The same processes that drive stars to form and collapse also allow neurons to fire, memories to form, identities to emerge. Nothing supernatural is required. No external meaning needs to be injected. The universe experiences itself wherever matter is arranged in a way that allows experience to occur. That experience does not have to last forever to matter. One of the quiet misunderstandings that causes so much unease is the idea that meaning requires permanence. That something must be preserved indefinitely to be real, to count, to matter. But permanence is not a requirement imposed by physics. It is a desire imposed by fear. Stars are meaningful without lasting forever. Galaxies are meaningful without being eternal. Patterns arise, persist for a time, then dissolve, making room for new ones. Meaning exists in participation, not in duration. Your identity is a process, not an object. It does not need to be frozen to be valid. It exists because a particular arrangement of matter holds long enough to generate continuity of experience. That continuity is fragile, but fragility does not negate reality. It defines it. When the arrangement ends, nothing essential is violated at the level the universe operates on. Matter continues. Energy redistributes. The system remains intact. What ends is not existence, but a specific configuration of it. Is not nihilism. It is relief. You are not required to justify your existence by lasting forever. You are not competing with eternity. You are participating in a moment that exists precisely because it is temporary. The universe is not asking you to endure indefinitely. It is allowing you to occur. That allowance is rare, not because the universe values rarity, but because the conditions required for complex experience are narrow. You exist at the intersection of countless processes aligning briefly enough to produce awareness. That alignment does not need a cosmic reason. Its improbability is enough. When you look at the stars now, the distance feels different. They are no longer decorations or abstractions. They are not symbols placed there for contemplation. They are relatives in process. Other arrangements of the same substance at different stages, under different pressures. Some of them are still burning. Some are already gone. Some have collapsed into states you cannot fully imagine. And here you are, in another phase entirely, made possible by what they did and what they became. This does not make the universe personal. It makes it intimate. There is peace in recognizing that nothing about you stands outside the system that produced you. No burden of exception. No requirement of special purpose. You do not have to be separate to be meaningful. You do not have to last forever to matter. Meaning emerges whenever experience occurs. It does not need permission from permanence. The universe does not rush to erase what ends. It absorbs it, it reuses it, it moves on without waste. You are part of that movement, not a passenger, not an observer. A participant. This does not diminish love, memory, or identity. It grounds them. It says they mattered because they happened, not because they were preserved. It says experience is enough. When this settles, something loosens, the need to stand apart. The fear of being small. The anxiety of impermanence. You begin to feel less like a fragile thing dropped into an indifferent universe and more like a local expression of something vast and ongoing. You are not separate from the stars. You are not watching the universe from the outside. You are the universe, briefly arranged in a way that can notice itself. And that is not a metaphor. It is what the physics has been saying all along.